Hello everyone. I'm going to talk a little bit about solving trig equations. First, I'm going to start by talking about the reasoning, and then after that I want to run through two examples. So to start with, let's think about a really simple equation, something that we have seen already in the past, but just using this to lead into what we're going to be looking at. So let's think about the equation the cosine of x is equal to 1/2. And we want to find the solutions for x. So what I'd like to do with this is I want to split this up, and let's take each side of the equation and think about the graph for each of those. So we have one where y is equal to the cosine of x, and then y is equal to 1/2. This represents a system of equations, and if we graph both of these, the points of intersection between those two graphs, those are going to represent the solutions to our original equation. So let's graph these and take a look at see what that looks like. So y is equal to the cosine of x. So that starts up at 1. And then, let's see, so then we go down to -1, back up to 2. So here's 1 period. And then I'll just go the other way as well. I'll do my best to connect these with a nice smooth curve. Okay. So this is our equation y is equal to the cosine of x. Now let's graph y is equal to 1/2. Y is equal to some number that is a horizontal line going through the y value of 1/2. So we have this horizontal line here. Okay. So everywhere where we have a point of intersection on both of these graphs, that represents a solution to our original equation. So as you can see, because the graph of cosine of x, because it has a period and it starts to repeat every 2 pi, and it goes on forever to positive infinity and to negative infinity, this equation actually has an infinite number of solutions. But there is a little bit of a pattern there. They do start to repeat. We get a solution at the same interval. So we see here, so we have this one, and then 2 pi units later, we have another one. If we start here, after 2 pi, we have another solution. So because of that period, it's easy to write out all of our solutions just using a multiple of 2 pi. So that's sort of the reason we're using it here. Kind of thinking about, okay, when is my cosine of x the same as 1/2? And then that gives us our solutions. So let's take a look at a couple examples. Okay. So in general, when I'm solving trig equations, the main thing I want to do is I want to isolate my trig, whatever term has my trig function in it. So in this first one, we have 4 sine of x is equal to 2 sine of x plus the square root of 2. So I have a couple different terms that have sine in them. I want to isolate the sine. If I can isolate the sine of x, and that's equal to some number, I can determine what my solution is. So start by rearranging this. I want to group everything that has a sine in it together. So I'm going to subtract 2 sine of x from both sides. These are like terms. It's just sine of x, it's sine to the first. So 4 minus 2, we get 2 sine of x is equal to the square root of 2. Now we have 2 times. I want to get this to be 1 sine of x, so to isolate that, we'll divide by 2. And we end up with sine of x is equal to the square root of 2 over 2. And to finish solving this, what we are looking for is what value of x, when I plug that into sine, is going to give me the square root of 2 over 2. Another way I could think about that is what angle, when I plug that in here, is going to give me this value. We know that sine basically represents the y value, so which angle is going to give me a y value of the square root of 2 over 2? We can use the unit circle to help us out with that, or we could think about it like we're taking the inverse of both sides. The only thing with the inverse is it does have a restricted domain, so it's not going to give us the infinite number of solutions that we want. But if we take a look at unit circle, so what angle is going to give me a y value of the square root of 2 over 2? So y value here, square root of 2 over 2, that's pi over 4. And then we have another one over here on this side, the symmetrical one, of 3 pi over 4. That also gives me a y value of square root of 2 over 2. So we have x is equal to pi over 4, and we also have 3 pi over 4. Now these are just 2 of the solutions. We actually have an infinite number of solutions. Because the period of sine is 2 pi, that means all of our solutions, we have pi over 4 plus 2 pi n, where n is some integer, so this is some multiple of 2 pi, or 3 pi over 4 plus 2 pi n. And I'll just say where n is an element of the integers. So now this covers all possibilities. Okay, let's take a look at our second one. 3 times the tangent squared of x minus 4 is equal to negative 3. Again, my main goal here is I want to isolate my trig term. So I want to isolate the tangent of x. So we have all of our algebraic properties and rules that we can use to help us out in that. In this case, because I have a tangent squared of x, I know I'm going to have to end up taking the square root of both sides to get that to be just tangent to the first. But first, let's isolate. So we'll start by adding 4 to both sides. 3 times the tangent squared of x. Negative 3 plus 4, we get 1. We have multiplication here, so to isolate, we'll divide by 3. So that leaves us with the tangent squared of x is equal to 1/3. Alright, so it's the tangent squared. I need that to be the tangent to the first, so we'll take the square root of both sides of our equation. So now we have the tangent of x is equal to, and then this is going to be 1 over the square root of 3, which if we rationalize that, we get the square root of 3 over 3. Okay. So now that we're isolated, again, to finish solving this, we're looking for the value of x, that when we plug that into the tangent, we end up with the square root of 3 over 3. Or what angle results in a value for the tangent of the square root of 3 over 3. Remember, tangent is y divided by x. So if we're looking at our unit circle, if I take y and divide it by x, when do I get the square root of 3 over 3? So y divided by x, so if I divide 1/2 by the square root of 3 over 2, that will simplify. So we have one solution at pi over 6. And then the next time that happens, so this one will be negative, which we don't want. And then negative divided by a positive, or negative divided by negative, gives me a positive, so our another possibility is 7 pi over 6. So we have pi over 6 as one possibility, and we have 7 pi over 6. Again, that's not the only possible solutions. In this case, the period for tangent is pi, so to cover all possible solutions, we want to add multiples of pi to this. So x is equal to pi over 6 plus pi times n, or we get 7 pi over 6 plus pi times n. Again, n is an element of the integers. So we're just adding multiples of pi. Okay. So there are two examples of solving trig equations. Again, the main idea here is we need to isolate our trig term first. Once that's isolated, we're just looking for basically the angle that is going to give us the value on the other side of the equation.